Welcome, everyone. I'm Brendan Hassett. I'm a professor of mathematics at Brown, and I'm the director of ICERM. So ICERM is the Institute for Computational Experimental Research in Mathematics. It's part of Brown University. Our core support is from the U.S. National Science Foundation, but we get additional funding from the Simons Foundation, Microsoft, National Security Agency, and other individuals and academic sponsors. We're interested in promoting positive feedback between mathematics and computation. So algorithms and software are important outcomes of mathematical research, and computational experiments are an inspiration and testing ground for mathematical ideas. So the impact of ICERM, is trying to develop that positive two-way street between these two subjects. We're also interested in the impact of algorithms and mathematics on society. And so this is, I think, what we'll hear about today. So Sharad Goel is an assistant professor at Stanford in the Department of Management Science and Engineering. He has courtesy appointments in computer science, sociology, and the law school. He studied at the University of Chicago and did a BS in mathematics. So I was also at the University of Chicago back then, and so it's nice to see how so many interesting things come out of our time there. He has a master's in computer science and a Ph.D. in applied mathematics from Cornell, and has worked at Microsoft Research in New York City. So his primary area of research is in computational social science. And so examples of this are in analyzing police practices using statistical tests for discrimination, fair machine learning for automated speech recognition, and of course, elections, analyzing swing voting, polling errors, voter fraud, and political polarization. So he started and directed the Stanford Computational Policy Lab, which is a team of researchers that address policy problems through technical innovation. One recent accomplishment is to deploy a blind charging platform in San Francisco to help mitigate racial bias in prosecutorial decisions. So he's been profiled, interviewed, and written essays for a lot of publicly prominent outlets like the New York Times, the Washington Post, Slate, the Huffington Post, This American Life, and the Boston Review. And so he's going to tell us about voting and how to determine whether one person is casting one vote. Thank you very much. Oh, and one more thing before. So we will be monitoring the Q&A and the chat. So if you have questions at any time, please feel free to put them in the Q&A in the chat feed, and we'll be happy to get them answered for you. All right, thank you.
Thanks, Brendan. Can everyone see my screen? Great. Okay. Thanks for that introduction. So just for a little bit of context, I want to start by telling you a little bit about this Stanford Computational Policy Lab that I started and direct that we heard just a little bit about before. So we're a bit of a unique institution or unique center among university centers, and that's because our stated mission is to drive social impact beyond the confines of a university, and we do that through technical innovation. We're an interdisciplinary group of folks, researchers, engineers, journalists that use technology to drive reform in criminal justice, in education, in healthcare, elections, and beyond. I'm going to talk mostly about our election work in today's talk, but before doing that, I want to tell you a little bit about this blind charging platform that Brendan alluded to at the beginning, just to give you a feel for the type of work that we're doing. So in the US, after someone's been arrested, the district attorney, a prosecutor in the district attorney's office, needs to make this high-stakes decision about whether or not to charge that individual with the alleged crime or not. And this is, there's quite a lot of discretion in this particular decision point in the justice system. And again, there are lots of consequences that flow from this one decision. So typically the way that this is made is that prosecutors are reading police narratives, they're looking at any other information that's been gathered at that time of arrest, but there's a worry that implicit or even explicit biases can creep into these decisions. And so we worked with one particular district attorney, the San Francisco District Attorney's Office, to roll out what we call a race-blind charging platform. So we developed a natural language processing tool that automatically masks the race and race-related proxies from police narratives. And so this tool is now being used in San Francisco to review incoming arrests for felony cases when deciding whether or not to file charges. So just to give you a brief example of what this looks like, here's a hypothetical narrative. These are all of this is fictitious, but you can see this is this type of information. This is the unredacted version where we have things like the officer's name, we have the neighborhood, we have the names of the other people involved, and even physical descriptors of those individuals. We automatically redact that to look like something like this version, where officer's name is replaced with officer one, the location is redacted, and then we see physical descriptors are redacted, but we try to preserve the kind of readability of this type of narrative. So again, this is just a very quick introduction to the type of work that we're doing in the lab, and especially on the criminal justice front, but it's a bit of a tangent from what I want to spend most of my time today talking with you all about. So one last thing I want to say is that this type of intervention, one thing that I really kind of like about this is that it's changing the way that we think of algorithmic interventions in the public policy sphere. And so this particular intervention has been getting a lot of traction. It's something we're trying to roll out all across the country, and is highlighting the ways that technology can be, when designed appropriately, can be used to improve these high stakes outcomes. Okay, so now I want to jump into the main topic of today.
May I ask one question from the chat, if that's okay?
Mm-hmm. Yes, please.
So there's a question about how to identify race proxies. What are the kinds of things that you look for in the reports that would be proxies for race or other demographic characteristics?
Yeah, so this is a really good question. We had long discussions with with prosecutors in the office and with other policymakers trying to understand what it is that we should redact. And so here we landed on redacting a few things. So the names in particular of the people involved, often names tell you that individual's race or ethnicity. We also decided to redact the names of the officers, because especially in jurisdictions like San Francisco that are a moderate side, about 1 million people, there's the prosecutors end up knowing which officers are stationed in which neighborhoods in a city. And so just seeing the officer's name will tell you the location. Knowing the location where an incident happened will tell you something about the demographics of the people involved. And so we redact the names of the officers. We redact the locations themselves. Obviously, physical descriptors we end up redacting. And at the end of the day, we try to estimate how much information is leaking through. And so so it's not perfect. So if I were to give you one narrative that I tell you the person involved was African American, and another narrative where I tell you the person involved was white, but I don't tell you which is which. So I say, so if you were to kind of guess at random, you would get that right 50% of the time. Here, we think a human can guess about 65% of the time which one involved the white individual and which one involved the African-American individual. And so it's not perfect, but we're trying to redact as much information as we can, but still makes it possible to make these informed decisions. So in that case, it's one particularly interesting thing about that is that some of the information that's leaking through is in the alleged offense. And so if I just know the alleged offense itself, that already tells me something about the race of the individuals involved. But that is something that's hard to redact when making this type of charging decision. And so there are kind of theoretical policy limits to how well one can mask race. But a really good question. Great. So now let's dive into the main part of today's talk. And so, like much of my research, this particular project started with a tweet. In this case, the tweet in question was by Donald Trump about 4 years ago. And he said, in addition to winning the Electoral College in a landslide, I won the popular vote if you deduct the millions of people who voted illegally. So what was he talking about here? Well, there are lots of, he's alluding to potential voter fraud, and there are lots of different types of potential voter fraud. So the ones that come to mind maybe quickly are double voting. So it's the same person voting twice. Voter impersonation. Sometimes this is colloquially considered dead people voting, non-citizen voting. And then aside from this type of what's called voter fraud, we also have the second category of what's commonly termed election fraud. That's not done at the scale of an individual, but is a little bit broader. And so this might be something like tampering with voting machines, destruction of ballots, tampering with the official vote count. And so one particular type of voter fraud that has been in the news quite a lot is double voting. And in this particular case, if you remember Dick Morris, he's a a GOP operative back, and when he was back in 2014, he was talking about the 2012 presidential election. He said this on Fox News: probably over 1 million people voted twice in this election, again referring to the 2012 election. So these claims of voter fraud, particularly double voting, have been around for quite a while. They've actually made it into the news even more recently in this particular cycle. And although this claim is kind of, I would say it's been around quite a lot in these GOP circles, in implicitly or explicitly alleging that this type of fraud is happening on behalf of the Democrats. Kind of, we had this sort of interesting, a little bit of a dizzying turn of events where Donald Trump himself seemed to be suggesting to people that they should double vote. And so this is a tweet that you may remember from just about a month ago. He says, to make sure your ballot counts, sign and send it in early when polls open. Go to your polling place to see if it was counted. If not, vote. Your signed ballot will not count because your vote has not been posted. Don't let them illegally take your vote away from you. So this was a particularly problematic statement, so much so that Twitter actually put a notice on this tweet. And because it was deemed as encouraging people to potentially vote twice. So this issue of double voting is quite serious, and it's not only been a hallmark of political discussion for the last couple decades. In this particular cycle, it's been quite prominent. So in part because of all this back and forth on double voting, it might not be so much of a surprise that a lot of the public, about a quarter of the public, believes that voting more than once happens either commonly or occasionally, as opposed to infrequently or never when given these four options. But just take a minute to think about this statistic. So in some way, this is, I would say, the most dramatic statistic that I'm going to show you in this talk. About a quarter of the public believes that double voting is either a common or occasional occurrence. Now, if you really believe that, that should give you serious pause for the integrity of American elections and more broadly of the democratic process writ large. And so this is an extremely troubling statistic. If people believe that this type of voter fraud is relatively common, that calls into question our entire form of governance and again, the integrity of elections. So this prompts the question is, how many people vote twice in a presidential election? And the spoiler alert is not a lot. I want to tell you this up front in case you get Zoom fatigue and you have to drop off after the next 2 minutes. I don't want you walking away thinking that double voting is a common phenomenon. So in fact, I'm going to spend the next kind of half hour trying to persuade you that this is a very rare phenomenon. And so again, just up front, double voting, despite the fact that claims of double voting are quite prominent, in fact, the actual evidence to support that claim is almost entirely absent. And I'll make a positive argument to say that we have strong evidence to believe that this is not happening very much at all. So again, that's our spoiler alert. So now, why is this? So this was quite kind of difficult to go through all these pieces, and I'm going to kind of explain the journey that we took over several years to come to that conclusion. This was joint with several people: Mark Meredith, a political scientist at Penn; Michael Morse, who's a political scientist, who's a political science grad student at Harvard and also a student at Yale Law School; David Rothschild at Microsoft Research; and a former PhD student of mine, Houshman Shirani-Meir at Stanford. And so when we started this work several years ago, the main statistical challenge is that there's no unique national identifier that links voting records across states. So for better or for worse, we can't easily tell if the exact same person has voted twice across state lines. So the only information that we consistently have available is someone's first name, their last name, and their exact date of birth. So that means the month, the day, and their year. So first name, last name, and their exact date of birth. But we don't know anything else about them. At least at scale, we don't really know anything else about them. And so this is the information that we have to work with. And so what do we do? Well, we'll start with the complete national record of voting. Of course, we don't know how anybody voted, but it's public record who has voted. And so for every time someone votes, again, we have these three pieces of information: their first name, their last name, and their exact date of birth. We have all that information. We have this compiled over the entire United States. I actually want to say this is quite difficult to compile this information, but in theory, it's all public and one can get access to it. So we have about 100 million plus records of all this information. So we just started with this massive data set, and then we started counting. We started counting all of these pairs of people with the exact same observable statistics: first name, last name, and date of birth. So we start counting and count. What do we find? We found 800,000 matches. So 800,000 pairs of people with the exact first name, last name, and date of birth. And at this point, we just kind of started scratching our head a little bit, and we're like, well, did we do this wrong? You know, we were kind of thinking this was going to be a weekend project. We're like, okay, we have all these claims floating around. We're just going to get the data. We're going to kind of end this debate, and we do this first pass. We're like 800,000 matches. We're like, oh, that's like a lot of matches. And in fact, it's like pretty close to what Dick Morris was alleging on Fox News a few years ago about 1 million double voters. And it's like, well, maybe something funny is actually going on here. Maybe there actually is a lot of double voting. Is that possible? Well, what do you think? What is your, and you can just kind of message us on the panelists side. What do you think is happening here? You know, we like double check the calculation and we end up seeing 800,000 matches. Any ideas what might be going on? So you can just enter in chat any thoughts. So one idea is, well, will people move? It's true. So I'm actually registered right now. I think I'm registered right now in New York. I actually live in California where I vote. And so people definitely move. So these are people who are not only registered, they're actually people who voted. And so lots of people are registered. There's lots of registrations. These are people who actually voted. And we have a kind of another thought here is that, in fact, these can just be coincidental matches. And this is like one of these funny things that, like, you know, someone already kind of used this phrase, the birthday problem, that I'm going to talk about in a minute. And so in some sense, we kind of know this idea that there can be lots of coincidental matches. And this is something that probably many of us on this call have encountered at some points in our lives. It's called the birthday paradox. But what's funny about this is, like, even though intellectually I know that's true, but now when you try to think about 1 million matches, 800,000 matches, that's a lot of matches. But we also have a lot of people. We have about 100 million people. And so, like, thinking through, does the math actually work out here? That feels funny. Like, it's like, are there really about 800,000 people out there that have the exact first name, last name, and date of birth? And so that's what I want to go through, is like, how do we actually understand the intuition of what's going on when we have these large number of massive, but also these large numbers of pools of people who are voting. Okay, so now I want to try to build a little bit of intuition by doing a quick interactive exercise. So in the Zoom room, I think we have about 150 people in this Zoom room. How many people have the exact same birthday? So here we're just going to do month and day. We're not going to do our name. We're just going to do month and day. We're not going to do year. And so let's find out. So there's, I think there's a Google Doc floating around here. It just got shared with everybody. So just click on that link, and you can log into that Google Doc and just put your birthday down under the right month and try to do this in order. And we're going to see how many matches we can find. So here, just go ahead and put, I already found a match for my birthday, June 15. I think there's another June 15 out there, whoever you are. And we'll try to see how many matches we actually can get. Lots of matches I'm seeing. We have a couple Jan 25s. What else do we have? My birthday, June 15th. We have a couple May 11th. So lots of double matches. We have a couple October 8ths. Do we have any triplets with this many people? There's a pretty good chance we're actually going to see a triplet. We have a couple July 6th. So lots of pairs of matches. So this again is just like kind of a fun exercise to try to get some intuition that, even in a moderate sized room, there's lots of double matches that just coincidentally occur. And of course, we're really talking about not just birth month and birth day, but really the exact first name, exact last name, and the exact year of birth. And so we're scaling this birthday problem up to this all these exact doppelgangers, but we also have many more people that we're potentially looking for matches over. Okay, so now let me go back to the real data. And so in the 2012 presidential election, this is the real numbers, these are real data, 141 ballots were cast by somebody named John Smith, born in 1970. Okay, so somebody with the name John Smith, who happened to be born in 1970, 141 of these people cast a ballot in the 2012 presidential election. Among these John Smiths born in 1970, 27 pairs had the exact same birth date. And so, for example, there were 27 pairs had the exact same first name, last name, year of birth, month, and day of birth. So really, these were doppelgangers, and they would be flagged naively as double votes. But if you work out the math, you would actually expect to see exactly 27 matches by chance alone. So again, this is the real data. These are the real. We went back to the voter file and we looked at this exact example. If we 27 matches by chance alone. So what's going on here? Again, how do we reason about why is it that you look at 141 and you're like, okay, well that's like a moderate size number of people, but 27, that feels like a lot of double matches in this room in this set of 141 people. So how does the birthday paradox work? And so let me just give you a little bit of quick intuition. Well, the idea is that there's lots of distinct pairs of people in any given room. So again, if we just forget about birthdays, we just take a room full of people, we have sort of lots of pairs of people. We have this pair, and we have this pair, and we have this pair. We have lots of different pairs of people. So if I just say count the number of pairs of people in any given room, there's lots of ways I can do that. In a room full of 141 people, remember this is the number of John Smiths born in 1970 that we have in our data. In a room full of 141 people, there are nearly 10,000 distinct pairs of people. Now, if I give you a pair of people, and I ask you, well, what is the probability that that pair of people has exactly the same birthday? Let's forget about year. All these people were born in 1970. So just ask the exact same birthday, the same month, and the same day. Well, the first person is born on some day, let's say January 1st. Well, the second person has a 1 in 365 chance of being born on the exact same day as that first person. So if I give you a pair of people, there's about a 1 in 365 chance that they share a birthday. But in a room full of 141 people, there are 10,000 distinct pairs of people. And so if I just multiply these 10,000 pairs with the chance that any one pair is a match, we actually get 27. And so this is where it's coming from. The idea that the number of pairs of people in a room is actually quite large, maybe larger than you might naively think, unless you kind of work it out explicitly. So even though the probability that any given pair is a match is relatively small, if you multiply it by this big number, 10,000 in this case, you end up with this number of 27. So again, that's just a little bit of intuition for where this birthday paradox is coming from. Okay, so we apply this birthday paradox. We generalize it up. We look at exact first names, exact last names, and we do this type of calculation that we did with John Smith. And what do we get? We get from 800,000 down to 29,000. And remember, about 100 million plus people were voting in the election, so 29,000 doesn't seem necessarily that far off. 800,000 feels like, it's like that seems quite large, or really a million people double voting. We didn't really know about it. But 29,000, it's like, that seems plausible. It's still like hard to detect things that are happening 29,000 out of 100 million times. And so it seems like maybe we're in the realm of possibility here. But something funny is still going on. So our simple calculation assumed that birthdays were uniformly distributed across the year. So remember, we said that a given match, if I give you two people, what's the likelihood that they were born on the same day? Well, we said that the first person was born in some particular day. The second person, again, had kind of a uniform chance of being born on any given day. And so it was about 1 in 365 that they were born on that particular day. That was the argument that we gave. And so we're assuming that these birthdays are sort of uniformly distributed across days. If we look at the data, that's not what actually happens. And so this is the real birthday distribution for one particular year. There are a couple things to notice. So it's showing the number of birthdays, the share of birthdays on any day of a particular year. There are a couple things to notice. The first, more people tend to be born in the fall than in any other time of the year. And what's quite striking is many more people tend to be born on weekdays than on weekends. So more people are being born on the weekdays than on the weekends. So what's going on here? So again, just like put your thoughts into chat. You can just like directly message this to us. What do you think is going on here? Why are more? That seems kind of, again, that's a little bit of a head scratcher. Like, why is it that people are more likely to be born on the weekdays than on weekends? Okay, good. We have some. Good. We have lots of good answers here. So again, one clarification is this isn't just saying that there are kind of more weekdays and weekends. So I'm not saying on average people, which is also true, people on average, if I had to guess, were you born on a weekday or a weekend, I'm going to guess a weekday just because there are more of them. In this particular case, I'm saying if I give you a particular weekend in a particular weekday, so here's a particular weekday, and here's a particular weekend, you're still more likely to be born on that particular weekday than on that particular weekend. And why is that? So we have a lot of good answers here in the chat. So we have C-sections, we have, we can induce births, so we can delay births just a little bit, so we can push things around. And so because we have a little bit of flexibility with modern medicine to shift when people are born, we have a preference for shifting that to the weekdays. Okay, so just like everybody else, doctors prefer working on the weekdays than on the weekends. And so we just shift everything over to the weekdays. And if we were to look at this plot back in like 1950, we would see a much flatter pattern. And so this is really a modern occurrence that we see this type of periodicity and this weekend effect. But why does this matter? So when you have non-uniformity, there are more coincidental matches. And so our estimate of double voting is going to decrease. So again, why is this the case? So suppose, and this isn't quite true, but just for an extreme case to build some intuition, suppose everybody was born uniformly on a weekday, not on a weekend. Everyone was born, like nobody was born on a weekend. We like always shifted these things. So no one was born on a weekend. Everyone was born on a weekday. We shifted these things. So everyone is uniformly born on a weekday. Well, there are about 260 weekdays in a year compared to 365 days in a year. And so in this case, any pair would have about 1 in 260 chance of sharing a birthday versus 1 in 365 chance of sharing a birthday. So again, this isn't quite true, but if we were to shift all of these birthdays to weekdays instead of uniformly across the year, we would see more coincidental matches, because now if I just give you two random people, we think, well, there's about a 1 in 260 chance that they happen to have the same birthday. So if I have more coincidental matches, then I would have fewer real matches left over.
May I ask you a question?
Yes, please.
Does the distribution, does it vary much from year to year, or is it pretty constant in time?
So the weekday weekend
Yeah.
is generally pretty constant in time, although there is this kind of decades-long shift in that we didn't see this pattern. And we certainly didn't see this pattern kind of 50, 60 years ago. But even over time, this has shifted a little bit until now we're at some sort of equilibrium. So we see this type of non-uniformity and matters quite a bit. Because it changes the number of coincidental matches that we expect. And if we change the number of coincidental matches, then we will decrease the number of real matches that we estimate from our data. So we do this we do this and we get from 29,000 to 26,000. Okay, and so we do all this work, we try to deal with this non-uniformity in the weekday weekend distribution. We get from 29,000 to 26,000. Okay, great. So that's like, like a 10% reduction in our estimated number of double votes. So it's non-trivial. It's something we have to be careful about. But then we realize, well, there's all sorts of other non-uniformity we might have to consider. So one other form of non-uniformity is that if your name is Deborah, there's a good chance that you're a baby boomer. If your name is Connor, there's a good chance that you're a millennial. And if your name is Katina, there's a very good chance that you were born in 1972. And so any idea what's going on with Katina? So not Katrina, Katina. If your name is Katina, if you ever meet a Katina, this is a good parlor trick. You can probably guess her birth year, 1972. So what's going on with Katina, 1972? Just like add your guesses to chat and we'll see what we get. Okay, so we have some pop culture, good. You're getting warmer here for bonus points. What was going on in 1972 with Katina? Getting closer, celebrity, famous person, almost there. Any soap opera fans, 1970s soap opera fans out there? Don't be ashamed if you know the answer to this question. We won't hold it against you. So this is so in 1972 there was a fictional baby born, quote unquote born, on a soap opera called Where the Heart Is. I don't think it's any longer in existence, this particular soap opera. And that baby's name was Katina. And so, which set off this flurry of real babies being named Katina in that same year. Okay, so all sorts of funniness is happening in these names. And again, this type of non-uniformity, so if you, into the extreme case, if I tell you here are two people whose names are Katina, then there's a pretty good chance, or a much higher chance that you would expect that they share the exact same birthday, because they already share the same year. Almost certainly they're going to share that same year. Okay, so this type of non-uniformity increases the likelihood of coincidental matches, will end up causing us to decrease our estimated number of double votes from the data. So then something else kind of funny happens with names. So if your name is June, perhaps unsurprisingly, you're quite likely to be born in June. If your name is Autumn, you're quite likely to be born in the fall. Again, for bonus points, if your name is Josephina, you're very likely to be born on one particular day of the year. Any guesses why that's the case? Josephinas are almost all born on the exact same day of the year. Why is that? So we got it. We got a couple correct answer here that this is Saint's Day, name's day for Saint Josephine. And for bonus points, anyone know the day, the actual day of the year that is? Maybe we have some Josephinas in the audience. Now I'm confusing myself. Someone says March 14th. I feel like the answer is March 19th, but maybe it is March 14th. I'm confusing myself. But we'll count that as a close enough answer. Okay, so again, it's it's always confirming March 19th. Okay, good. So that is the namesday for Josephina. And so again, this type of non-uniformity really can affect the number of double matches. Again, if I give you two people, or if I say here's a pair of people named June, again, there's a pretty good chance that they share the same birthday because they already likely share that same birth month. So we saw this and we're like, okay, we should take care of this, but how big a deal can this really be? It's like, yeah, June, autumn, I get it. Josephina, there are these name days. Okay, maybe there are a few of these we have to take care of, but how big an effect can this really have? And so I was like, okay, well, let's just take a regular name. I was thinking of my father-in-law at the time, and I was like, okay, his name is George. And it's like, well, that's like a regular name. Georges are just going to be uniformly spread across the whole year. So we went to the data, and we found that actually that's not true. So George, again, this was just kind of, I kind of lost a bet here. And I was like, George, there can't be anything special about this name. And George turns out to be born, Georges tend to be born on one particular day of the year. So what is that? day of the year? Anyone want to guess? Again, in chat, just put your answers. It's a pretty strong effect. What's the most common day of the year for a George to be born on? So here we have some good guesses. So February 22nd, George Washington's birthday, President's Day. I asked this once before, and people said President's Day, George Bush's birthday. And it's like, no, President's Day is not George Bush's birthday, it's George Washington's birthday. So just a little bit of extra history there. We have Georges are more likely to be born on this particular day. And it turns out that lots of names actually have these funny patterns to it. So what is the most common day of the year for Carols to be born on? Any guesses for this? Again, put it in chat. Most common day of the year for Carols to be born on. Good, we got lots of correct answers here. So Christmas Day, December 25th. So really, we were not trying to cherry pick these. We were just like putting out names. We're like, okay, Josephina name day, I get it. June, I get it. Autumn, I get it. But let's just like think of, just regular names, and we will. What we were quite surprised about is finding that, in fact, many of these names have these funny patterns associated with. So this is a real issue that we have to adjust for non-uniformity in the names that parents decide to give to their children. And so our goal here is to estimate the distribution of birthdays for every name. And the problem is that even with 100 million records, we can't really do this. And we have this not only for like one election cycle, we have it for many election cycles. And so we have hundreds of millions of names out there, but it's very hard to directly estimate the empirical distribution, accurately estimate the empirical birthday distribution for any given name. There are lots of names out there. So what do? So here we're going to have to make a couple assumptions to try to get at this estimate. So our first assumption is that birthdays and birthday of week are independent. Oh, someone just put in chat that their name is Maya and that they were born in May. So I think that's another nice example of this phenomenon. So back to our main assumptions here. So birthday and birthday of week are independent. We can verify this in the data that if I tell you that your birth date, so I was born on June 15th, you basically can't tell from that information alone what day of the week I was born on. If I tell you the year, of course you can do it, but if I just tell you birth date, you can't tell me the day of week that I was born on. So this is our first assumption that we're going to make. The second assumption we're going to make is that if 2 years have the same weekday schedule, then the distribution of birthdays for a given first name is roughly the same in both years. So what does this mean? So if I say here are 2 years with the same weekday schedule, meaning that January 1st on both of those years is the same. So let's say January 1st is a Monday, and neither of these are leap years, let's say just for simplicity. So if I give you any other day of the year, then if that day happens to be a Monday in one year, then it happens to also be a Monday in the other year. So that's what I mean that they have parallel weekday schedules. So if I take 2 of these years that have parallel weekday schedules, then the distribution of birthdays in 1 year is the same as the distribution of birthdays in the other year. So a certain number of Georges, a certain fraction of Georges that are born in 1 year on February 22nd is the same as the fraction of Georges that were born on February 22nd in the second year. There's going to be a spike in both of those years. And if I take another random day, if I take May 17 in both of those years, again, the same fraction of Georges are going to be born in those 2 years. So that's all I mean here. So I'm not precluding the popularity of a name changing over time. I'm just saying the distribution of that name is the same in these 2 years with parallel weekday schedules. Now, the final assumption I'm going to make is that for any fixed day, the distribution of first names is independent of the day of week. So this is a little bit funny one. So let's say that, again, I was born on June 15th. And so we said, just like, let's look at June 15th. And now if you tell me somebody's name, I still can't tell you very much about the day of the week on which they were born. So intuitively, that seems plausible for the most part, except for there's some funny examples So can anybody think of an example where if you tell me their name, I can actually guess the day of week pretty well? Again, just put this in chat. Any ideas here? Yeah, so we have lots of good answers. So if your name is Friday or Wednesday or Tuesday or any of these like day of week names, there's a pretty good chance that you can guess the day of week that they were born on just from their name itself. So we're going to assume that even though this isn't strictly true, this is a relatively rare phenomenon. Again, empirically, we can check that that's the case. So we have these three big assumptions on the relationship between names and the days on which people are born with those names. And they're not exactly true, but we think they're approximately true here. And when we do this, then we can decompose the distribution of names over the year into a day of year effect and a day of week effect. So the day of year effect is something like this February 22nd phenomenon for George Washington or December 25th phenomenon for Carol. And the day of week effect is, again, saying that people are more likely to be born on weekdays than on weekends. So with these three assumptions, mathematically, we can show if these things hold exactly, then we can perfectly decompose these birthday distributions into these two components. And it turns out that these two components are much easier to estimate than that full birthday distribution on its own. So we go through all of these steps, and what do we get? We go from 26,000 down to 21,000. So we started out with 800,000 double matches where we're like, oh, is Dick Morris really right? Then we do this kind of classic birthday correction down to 29,000. Then we realize, well, classic birthday correction assumes that things are uniform across the entire year. Really, babies are more likely to be born on weekdays than on weekends. So we get down to 26,000. Then we realize that names themselves give a lot of information about when someone is born. Junes are born in June. Augusts tend to be born in the fall. Georges tend to be born on February 22nd, et cetera. So accounting for all of that, we get down to 21,000. And at this point, we're about 2 years into the project. And we were like, really, like we've been like, hammering this problem for a couple of years. We really thought this was going to be a weekend effort. That was obviously naive in retrospect. Nothing I've done has ever been accomplished in a weekend. And so we do all this stuff. We get to 21,000. We're tired. And we're like, okay, well, this is the answer. So, we got to 21,000. 100 million people voted. It seems totally plausible that there are 20,000 double votes out there. And we're getting ready to publish our paper, to announce our results. And then we had a bit of an epiphany of saying, well, what about potential errors in the vote record itself? And so almost all of my work, we start with these large data sets. So in this case, we started with 100 million digital records of voting across the country. We do all this analysis and we get some number. And so it's even occurred to me that we have to worry about errors in that original data set. But now when we're trying to estimate things that are on the order of 1 in 10,000, 1 in 100,000, small errors in your data really matter. So let's just so first of all, how can errors crop into this type of data set? Well, so this varies across the country, but in many jurisdictions, you have poll books that look like this, where you have somebody signing when they vote next to their name. And then you see these barcodes over on the other side, and a poll worker goes and scans these barcodes, and that's how this paper record of voting gets translated to a digital record of voting. Now you can imagine you're standing there all day. Well, maybe you scan the name above or below the actual name where somebody signed and the person who actually voted. And so there could be small errors in this process of going from the paper record to the digital record, and these small errors can add up. So let's just get a little bit of intuition of how this can work. So using a similar birthday paradox correction, we estimate about 2 million voters have an unused registration in another state. So I'm one of those 2 million people. So I used to live in New York. And so right now I'm likely on a poll book in New York. And so even though I don't vote in New York, I'm on the poll book. So if somebody goes in and they sign underneath my name, there's a chance that the poll worker will scan my name in New York. I vote in California. And if this this sequence of events happens, I would be flagged as a double voter. So if that happens 1% of the time, so if 1% of these deadwood registrations were mistakenly marked as having voted, that would explain almost all of these 20,000 double votes that we saw in the data. Right? So if you have 2 million of these things, which we can estimate from the data, and if you have this 1% error rate, which we haven't estimated, I'm just saying hypothetically, if we saw a 1% error rate in this procedure from going from paper records to digital record, that would account for almost all of these ostensible double votes that we see. So how do we estimate this? It's very hard to estimate the actual error rate because voting procedures vary quite widely all across the country, but we tried. We manually verified the accuracy of 30,000 vote records. We sent a team of undergrads to Philly to go to the polling place. I was kind of, again, naive. I was thinking, oh, we'll just sort of do this electronically. We use all this, we're computer sscientists. We have all these fancy methods for doing. We're just going to go in. We're going to bring in our scanners. We're going to do some OCR. We're going to figure out exactly. We're going to match the paper record to the digital record. And we get there and we're like, well, you can't bring anything electronic into the records office. So no phones, no computers. All you can do is bring in some paper and some pencils. And so this, we have to retool, and we're figuring out, okay, well, I guess we really have to do this manually, and just kind of using the buddy system here of saying, here is a list of 30,000 records. We know what's going on in the electronic record, and we manually go through. When I say we here, I really don't mean me. I mean the students that very kind of graciously did this, and they manually verified these 30,000 records in 47 randomly selected precincts in Philly. What was the answer? They estimated about a 1% error rate in registrations. About 1% of these things that had an electronic record of voting, but no corresponding signature. And so likely there's a good chance that those people actually didn't vote, even though they were marked in the electronic record of voting. Okay, so we do all of this work, and now we're down to about epsilon here. So 800,000 down to 29,000, we account for kind of classic birthday coincidences, down to 26,000 when we account for the weekday, weekend patterns, 21,000 when we account for these funny patterns of names and when people are born, down to epsilon again here. I don't really know what the true answer is. Philly is not the entire country, so we have a good estimate of what's going on for Philly. We don't really know what's going on in the rest of the country, so it's somewhere between 0 and 21,000. I would say it's on the epsilon side of that spectrum, whatever that means, but we think it's a relatively small number of actual double votes that are going on. So this result, in some ways, we ended up back where we started, where we're like, well, there's no way there are a million people who double voted out there. And we're just kind of using our intuition and saying, okay, well, there can't be a million people. That just feels like there's too many. We would know if that's true. But now we're going through all this rigmarole. A few years later, we actually have this reasonably tight estimate of 0, and there are pretty serious policy implications for this result. So first, I want to flag that there's always this trade-off between voter accessibility and election security. And so as we make our elections more secure, we're often making it harder for people to vote, and vice versa. And so if we have things like same-day registration, or if we require identification when we're voting, in some ways, we're changing the security of the election, but we're also changing the accessibility of voting. And so I want to be clear here that there is a trade-off. At the same time, if we crack down on a phenomenon like double voting that's extremely rare, then we can unjustifiably disenfranchise many legitimate voters. And so this is really happening. And so the way that we estimated this is that there's this program called Crosscheck, where states voluntarily send their registration data to Crosscheck that matches records between participating states and sends back a list of potential double voters based on matching first name, last name, and date of birth. And now in those states, the secretaries of state can decide to purge those voters from their voting rolls when they see these potential double matches. And so we obtained the data prior to the 2012 election in Iowa. We merged it with our voter file that we have to see who among these people are actually voting, and what are the implications of this type of purging strategy. So the first thing that we realized is that first we limited to people where we had their social security number, at least the last 4 digits of their social security number. And we found that many of these double matches that were being returned by Crosscheck, they actually matched on the last 4 digits of their social security number. And so these really are the same people. They're likely the same people. But remember, these are registrants, not voters. And so Crosscheck is returning double registrants in theory, not double voters. They don't know the double voters so easily. They only know the double registrants. And so, for example, I'm a double registrant. I'm voted. It's perfectly legal. I'm registered in New York. I'm also registered in California. And so I would be in this list if New York and California participated. So we looked at these double registrants, and we actually figured out which of these pairs of people were voting. Which of these people were voting. And we found that only in 7 of these instances, 7 of these 26,000 instances, was there a double vote. And what's quite striking, in 2,500 of these instances, the earlier registration was used to cast a ballot. So what does that mean? So one, you would think kind of reasonable policy is let's just purge the earlier registration. So in my case, that would be fine. Like if New York decided to purge my record, that'd be fine. I registered in New York earlier, then I moved to California, I registered in California, I vote in California. It wouldn't be a big deal to me if my record in New York were purged. But in 2,500 of these instances, the earlier registration was being used to vote. And only in 7 of these instances were actually both of these registrations being used to vote. So in this particular case, to catch 7 people for double voting, we're actually making it quite difficult for 2,500 people to vote legitimately. And so this trade-off of about 300 to 1 is quite, is quite traumatic. And it kind of, even if you understand that there's this trade-off between accessibility and security, this, at least in my mind, is too extreme to be trying to prevent this phenomenon that we now have evidence to believe is really happening quite rarely. So now, just in summary, I want to kind of highlight this one thing that I alluded to, but it was really a little bit surprising to me, is that when we started this project, our intuition was based on the fact that if double voting were rampant, we would know it. We would catch some of these double voters. And so we're really trying to prove the absence of something. And the idea was, well, if we look really, really hard, if we don't see it, then that's strong evidence that the phenomenon is not happening. And the retort to that type of argument is always, well, you haven't looked enough, or people are just too clever for you to find them. But what we actually did at the end was something quite different. We found strong statistical evidence, positive statistical evidence, that double voting is rare. It's not that we looked and looked and looked and couldn't find it, but rather we found positive statistical evidence that something was rare. And so this was a quite different kind of epistemological way of thinking about this problem, is that it's not that we're convinced by finding an absence of something. We found positive evidence that something is not there to be found. The second big point I want to make, again, is what we just talked about, is that attempts to curb double voting, for example, via Crosscheck, can disenfranchise a large number of legitimate voters. So not just in theory, but also in practice. So we really have to balance how much we try to increase election security with these, in some cases unintended, in other cases actually intended attempts to disenfranchise large segments of the population. So I'll stop with that. If you're interested in reading more about this, please check out this paper, One Person, One Vote, joint with my fantastic collaborators, Mark Meredith, Michael Morse, David Rothschild, and Hushman Shirini Mer. And please get out the vote. Please vote yourself. Encourage your friends and family to do the same. Our democracy is stronger when we all participate. So I hope you all have voted already or are in the process of voting, encouraging others to vote. And finally, if you're broadly interested in this intersection of computational ideas with policy, please check out the work that we're doing at the Policy Lab. We have lots of information there for folks to read up on. So I'll end with that. Thanks again for your attention.
Thank you, and at least I'll clap. So there's a note that was really interesting and quite I've never seen so much chat and they talk. Yeah, we'll have to use you as an example. It's really wonderful. There's a couple questions that came up. So one person asked to hear more about exactly how the compressions from 800,000 to 29,000 to 26,000. I think you explained it, but maybe you could just sort of recapitulate that point.
Yeah, it's a really good question. It's hard to keep track of all the numbers. So let me see if I can do this without a reshare. Well, no. Well, yeah. Okay. Let me try to do this by memory. So we had 800,000 to 29,000. That was this idea that just kind of more or less classic birthday problem, textbook birthday problem of saying that if you have, roughly 100 million people in a room, then this is the number of, you're going to have something like 750,000 double matches. And that's how we get from the 800,000 matches to 29,000 matches. And now when we're trying to get from 29,000 to 26,000, that was based on this observation that people are more likely to be born on weekends or weekdays than on weekends. And so if I have non-uniformity there, then I have more coincidental matches, which means I'm going to lower my estimate of kind of real matches. So now going from 26,000 to 21,000, there the idea was that if I tell you somebody's name, then I actually know a lot about their birthday. If I tell you somebody's name is George, there is a pretty good chance that they're born on February 22nd. If I tell you someone's name is June, there's a pretty good chance that they're born in June. And so again, this type of non-uniformity means that I'm going to have more coincidental matches, fewer estimated matches. And now to go from 21,000 down to epsilon, that was this idea that even small errors in the digital record itself can have large implications. So we estimate about 2 million deadwood registrations out there. So people that are registered in multiple jurisdictions. Again, I'm an example of this. This is totally illegal thing to do. It's like when you move, you don't have to purge your registration in another state. And so when people are on poll books in two separate places, if there's small errors in recording who has voted, that could lead to large discrepancies in our estimates of double voting. And in this case, we estimate that gets us from about 20,000 down to approximately 0 real double votes that are happening.
Another question that was asked is, and so this is outside the statistical analysis that you brought up, but I think I mentioned it. How about the policy reasons for purging multiple registrations? For instance, if someone has multiple registrations, they're basically given an option to vote and where they think their vote would have most value, or, I mean, there's lots of policy reasons to do that. So can you comment on those?
Yeah. So again, I want to make sure that I don't come off as kind of glib here when I say that there is this real trade-off between election security and voter accessibility. Like, this is real, and we have to decide as a society, where do we land on this spectrum in any one of these decisions? And this comes up not only in voter purging to make sure that we have kind of clean poll books, but also when we're talking about policies like voter ID laws and same-day registration and other policies like this. So I think there's a real conversation that we have to have about where we draw that line. In this particular case, I think it's important to recognize that this idea of double voting, even though a quarter of the population believes it to be a widespread phenomenon, and we have prominent politicians kind of promoting this idea that it's a serious threat to democratic governance, we not only don't have evidence of that happening, so very few people have been caught double voting, we in fact have positive statistical evidence this is a very rare phenomenon. So when that's the case, I think that shifts, for me personally, it shifts the, kind of tips the scales and saying, if we are going to make it harder for people to vote predicated on this idea that there is widespread double voting, I personally would caution against that style of argument. In this case, we have very little reason to believe that this is a problem. Double voting is a problem. And the direct implication of that is efforts to correct that problem can disenfranchise large numbers of voters.
So there was a question about the data for names and dates of birth. Where did that data come from? Was it the census? Was it other sources?
Yeah, so here we're directly using our voter file. And so so we started out with this collection of 100 million plus people where we know exactly the first name, last name, and date of birth of everybody who voted. So we did everything internally in that data set. So everything was targeted at that set of voters.
So there was a question, so for the Ohio Crosscheck analysis, so exactly how did you verify where people voted? Was that, yeah, can you say a little bit more about that?
Yeah, so Ohio is nice. So we were able to get a voter file from Ohio, and and we also have things like Social Security matches, and so it's easier. But with this additional information, it's easier to figure out definitively whether two people are the same. And so it's not just first name, last name, and date of birth, but we have, for example, there's local voter ID number, which we can match given a local voter file. So even though we can't do this perfectly across the country, in local jurisdictions, we're able to do this with more accuracy.
So people ask about other ways of cheating in elections, like ballot tampering or stuffing ballot boxes. Of course, not all these things can be addressed through statistical means, but is there like a next problem that you think is amenable to this kind of investigation?
Yeah, I mean, I think this idea of non-citizen voting, which is this sort of pernicious idea that keeps on cropping up, that again, the claim is that there are many non-citizens who are casting ballots, which again, there's very little evidence that this is happening. My guess is this type of approach can be used to statistically think about that question and find positive evidence, again, assuming that's the case, that this is a very rare phenomenon.
So there was a question about whether it would be possible to actually do real-time analysis of elections as they happen to determine whether whether things are being done improperly in real time, or is that just impractical?
Yeah, I mean, so there are especially in this particular cycle with so much early voting, I mean, real time election tracking is certainly possible, and this is part of what I think we're already starting to see early returns of this. This is coming through the same sort of voter files that we look at, where you can see the number of mail-in ballots that have been cast. And that information is available in roughly real time. And so I think some of this can be happening. There's probably going to be more of a shift to that as voting early and vote by mail becomes more common.
I'm going to ask one more question. Many of the people who are watching this are people working in math or statistics or computer science. So what is a simple case that you can make to people who aren't already steeped in these techniques for why double voting is rare? So can you sort of summarize it in a way that we could communicate to people at cocktail parties, or what's a...
Yeah, so it's a really good question. And so one thing is, it's like, if you really believe, nobody should believe that 1 million people have double voted, because there's like no positive evidence, or there are very few documented cases of people double voting. So even without the statistics, these claims of widespread double voting seem quite unlikely, because the fact that we just haven't observed it. And so now how do you go from 1 million to 20,000 to 0? That's hard. And I'm not sure, it's like, even my intuition is like, before we did this careful calculation, I was like, well, maybe there are 50,000 people out there. It's like, even when I saw this 800,000 number, I was like, oh, does like the birthday paradox really account for 800,000 people? Like, I just sort of intuitively think, well, how many Sharad Goels can there be born on June 15th in 1977? I'm like, that's like extremely rare event. It's like hard for me to get intuition about all this type of cancellation that's happening. And so I think that's like genuinely a hard problem. So even though intellectually I know this can happen, I think it is very difficult to convey that type of information. We have tried to, so I think unfortunately there's not a sort of tweetable version of like, look, here is a one-line argument for saying why there's almost certainly not widespread. There's not like double voting on the scale of tens of thousands of people even. We did try to write our paper in a way that is broadly accessible. And so we had that in mind, that we're trying to reach a broad audience of people who might not necessarily read academic papers. And so hopefully we did an okay job at that. So, please point people to that work if that's something that you think might be persuasive.
Okay. Well, there's still tons of questions, but I think I will I'll bring this to an end. So thank you very much, Professor Goel. It was a really wonderful talk and just what we need to hear in the season. And thank you for all the people that commented and contributed to the Google Doc and asked questions. It was you added a lot to the lecture. So we have another lecture on a somewhat related topic scheduled for next week. So Jonathan Mattingly will speak on gerrymandering, with a view towards redistricting decisions in the coming years after the current census. And so he'll speak next Wednesday, the 28th of October. So please come back if you enjoy this. We'll also have a panel of experts from various fields, from law, from political science, and from other areas to discuss the implications of the census for drawing future districts. So please come back for the second round of our election season public policy and public outreach lectures. Thank you, everyone. Take care. Bye-bye.